Hey, thank you for the kind introduction and welcome everyone this morning. So today I want to speak a little bit about why federated learning at all, why should you care about this, then give an intro into how this works fundamentally to give you some intuition, and then also show how this works, how you can implement your first federated learning project rather easily using the Flower Federated Learning Framework. So let's jump right in. So first of all, why should you actually look at federated learning, and why is it crucial for the future of data science? Today we're in the situation where most of the models that we train them on public and or centralized data. And public data and centralized data is only just a tiny fraction of all the data we have in the world. There's much more data that is sensitive and is distributed. It's distributed across different organizations and it's distributed across different user devices. But it's not being used to train major AI models today. So the fundamental reason for this is that data, when it originates, it's just naturally and fundamentally distributed. Data originates on different user devices, for example, by the user interacting with some application. Data originates in different organizations. So the natural state of data is that it's decentralized. Now, the way we train AI models today is we just train a model on just one of these partitions. We train the model on the data that, for example, a single organization holds internally, but all of the other data is ignored. So the question is, sometimes we discuss this, are we GPU rich or are we GPU poor? I think the more important question is actually, are we data rich or are we data poor? So the current approach, as you can see, because we just use a single one of these data partitions, seems fairly data poor to me. So what organizations are trying to do in order to overcome this limitation is they try to make this single partition bigger by collecting more data into the single partition. So they try to collect more user data, or they try to strike licensing deals with other organizations that have some data that they're willing to open up and willing to hand over to that other organization to help them make this single partition bigger and then to train a slightly better model because we have more data in this single partition. Fundamentally, it doesn't solve the issue because it's just unrealistic to assume that we'll be able to license all of the data that we have. And there's many things that are sort of preventing us from doing this. Data just fundamentally is difficult to move. There's regulations in place that actually prevent you from moving data out of different regions. There's privacy concerns. Sometimes there's also just practical concerns. I recently heard of an organization that processes more video data on the edge than YouTube does in a single day. So imagine moving all of this data volume, moving all of this to the cloud for model training is just not practical. Now, this begs the question, what would a data-rich future for AI actually look like? And probably given the image we've seen before, it's probably obvious that it would look something like this. It will look something like this. We have data in different partitions. We have data in different regions around the world. We have data on different user devices. And what we would try to do is we would try to connect those different data partitions, those different data sets. And we would try to form a network out of all of these and then try to train on all of these for a little bit. And we would try to collect all of the learning results. Well, this is actually what federated learning is all about. And we'll go into how this works in a second. So just fundamentally, federated AI creates this capability for us to access more training data. The traditional way, as we described, used to be collect all of the data, move the data to the computation. So we're collecting data from user devices onto a server, and then on that server, we would train the model. The issue is data needs to move, and as we've seen, it's difficult for data to move. Regulations, privacy, practical reasons. There's many reasons why data cannot or must not move. So Federated AI gives you this capability, and Federated AI says, let's just flip this. Instead of moving the data to the computation, let's move the computation to where the data already is. And by doing that, the data stays where it originates. It stays on different user devices. It stays within different organizations. And then by moving the computation there, we create this fundamental capability to access more data in our training runs. Now, one perspective on this is software frameworks like PyTorch have created this ability for us to relatively easy train models on thousands of GPUs today. Now, the next step is to create a software infrastructure that allows you to train models on a large number of devices in the future. This is where federated learning comes into play. So let's go into how this works in detail, step by step. We start out with a machine learning model, maybe a neural network, maybe some other kind of model on the server side. This model is randomly initialized, so it doesn't have any knowledge of anything yet. We take this model, we send it to all of the participating devices. So in this case, we have a number of mobile devices, 3 mobile devices. We send the model, the exact same copy of the model to all of these mobile devices. And then each mobile device trains for a little while on their local data set. So each of these devices trains maybe just a single epoch. It doesn't train the model to full convergence, but only a little while. This ends up giving us 3 different models. Each device has a different local data set. So if they take the same model and then train it for a little while on their local data set, we'll end up with 3 different models. And then the last step, well, the second to last step is to communicate those updated models, those 3 individual models, back to the server. Now the server has now 3 different models. And but what we want is one single model that has the learnings from all of those devices. So the last step, the final step, is to aggregate all of those models together into one single model. The easiest way to do this is to do a weighted average. Average the models weighted by the number of training examples on a single device. But there's many different approaches for aggregating models. So this is practically vanilla federated learning as it was introduced by a paper from McMahon et al. In 2017. And the paper is fairly readable. I can highly recommend reading the paper. And it essentially does a basically standard SGD on the client side, where you update a model on the local data. And then there's sort of this outer optimization step that happens on the server side, where you would initialize the model parameters, send them to all the devices, get back the pseudo gradients from those devices, and aggregate them in some way. This is the vanilla federated averaging paper. I can highly recommend taking a look at it. It's a pretty readable paper, and by now it's a classic in the federated learning, in the world of federated learning. So here's a small animation that shows how to do this, how this happens. We could see that the server has this initial version of the model. The model then moves to the participating devices. The participating devices train the model for a little while on their local data, and then move all of the updated results back to the server. And the server then finally aggregates them. The interesting thing is that in the end, we end up with a model that has the learnings from all of those devices without the server having seen any of the training data. Now, in addition to federated learning, there's also federated evaluation. In federated evaluation, we also send the model to those devices, but then we only evaluate the model on those devices. We don't train the model on the local data. we just use the local data to evaluate the model. And what we send back to the server are evaluation results like the loss on the local data or the accuracy on the local data. In addition to federated learning, federated evaluation, there's also federated analytics. In this case, we don't even send a model to those devices, but we send something more like a SQL query, some analytical query that we want each device to execute, and then we collect the analytical results back and aggregate them. This gives the server an sort of a global result over all the local data sets. And if we combine this with things like secure aggregation, the server can then only read the aggregated update. So this can work well, for example, across different organizations. Maybe there's different healthcare institutions, and we want to calculate the average age of a person getting a certain kind of disease. By doing this, by using federated analytics, we can calculate this across all participating organizations without a single organization having to reveal anything about themselves. Now, I should also add that while federated approaches give us powerful capabilities, there's also no free lunch. So there's a couple of things. If we want to have a secure and private solution, we can only achieve it with a careful and holistic design. So oftentimes federated approaches, they create this fundamental capability for us, but then we want to carefully combine them with certain things like differential privacy. In some situations, we want to use secure aggregation and things like that to really make it an end-to-end private and secure system. With that, let's talk a little bit about Flower. Flower is a leading federated AI ecosystem. The Flower framework, what we try to do fundamentally with the open source framework we're building is we try to give you a unified approach to federated learning, analytics, evaluation, and then also related approaches that are not strictly federated, but that sort of require exactly the same infrastructure. Things like fleet learning or also some kind of cyclic training, things like that. Now, in order to do that, there's quite a bit of complexity if you want to move models around and if you want to move the computation around and involve different kinds of devices. You want to support different platforms like Android and iOS. You want to support different learning schemes across silo, cross device, horizontal, federated, vertical federated learning. You also want to support privacy enhancing technologies, differential privacy, secure aggregation, secure multi-party computation. And Flower tries to give you all of this in a nice and easy, unified kind of API. Flower is also open source under the Apache 2.0 license, and it's completely model and training framework agnostic. So you can combine Flower with the tools, with the frameworks you already like, with the frameworks like PyTorch, MLX, and TensorFlow. And you can also combine it with any kind of model. You can use small neural networks, larger ones. You can also use different kinds of models, like tree-based models, for example. And then fundamentally, what Flower gives you is this idea of going from first idea all the way to production, deployment, and operation. So usually you want to start out, you have an idea, you want to start out on a single machine, iterate on the idea quickly, then maybe simulate it on a larger cluster. Remember, these systems can get very large. So in production deployments, there's some of these systems have hundreds of millions of clients participating in a single training run. And then after simulation, obviously you will also want to deploy this in the real world, either across a fleet of devices or a fleet of different organizations that are working together. Now, as I mentioned already, Flower has a fairly large ecosystem, so it combines well with all the tools you already know and love. Many of these integrations are actually not built by the core Flower maintainers, but there's a large community around Flower that builds these integrations and that is working with us to make Flower integrate nicely with those other tools. Sometimes we also use the Flower framework ourselves to push the boundary of what's possible. So one of the recent announcements we had was Flower LLM, the 3 billion parameter version of it. So we use Flower ourselves to train a model on completely decentralized data. In this world of training a model on completely decentralized data, federated data, Flower LLM 3B is the largest model that has been trained in such a setting. In addition to the framework and Flower LLM, we also have some other efforts. Flower Baselines is one of them. Flower Baselines is a bigger effort where the Flower community reproduces interesting research results and sort of puts them all into an easy-to-use package. If you ever read a paper and wanted to improve upon the paper, and then first had to start with reproducing what that paper has done, you probably have experienced that reproducing whatever someone else has done is probably 80% of the work, and then the original idea you had probably takes very little time compared to that original reproduction. So what the Flower community is doing with Flower Baselines is it does the reproduction part for you, and then you can simply take that and immediately start working on your ideas. With that, let's go into a quick hands-on and show what using Flower actually looks like. So the easiest way to get started is to just do a pip install Flower with the simulation extra. So the package name is FLWR. Then do FLWR new, which guides you through the creation of a new project. And then do a FLWR run. And I'm going to show that now live. So I'm going to make this a little bit bigger so that everyone can see it. Hoping that this is big enough. So in this directory, I'm going to use, I've already installed Flower, so I'm doing an FLWR new. I need to give a name to this. And then I'm going to type my username, and I'm going to use the MLX framework in this case. So this gives me some instructions on how to now install the project. So we go into the ODS SC package. We do a regular pip install -e. So that installs all of the dependencies we need for the project. And with that, we can already do a FLWR run. I'm going to show that project before I'm going to run it, just so that you can see what the project looks like. So I think that one, I should also make it a little bit bigger so that everyone can see it. What this gives us is a simple README with all the instructions on how to install and how to run the project. It gives us a PyProject TOML with all the dependencies for the project and some Flower-specific configurations. For example, when we run this on a local machine, we can simulate a number of nodes so that we don't have to actually start that many machines. In this case, I'm just going to use 3 nodes. So I'm simulating a setup with 3 different data partitions. And then in the coding part, there's a regular task.py. So this contains your model architecture. It contains the code to train and evaluate the model, and it contains the data loading that would happen on that particular client. And then the 2 things that are Flower specific are server app and client app. Those are relatively short scripts in this case. You can make these more complex and customize more aspects, but in the easiest case, they're pretty short and they just use some defaults. So client app in particular is interesting because this is where you connect whatever you have in your task, like the model architecture and the data loading, to the Flower framework. And to do that, you would you would implement what is called a Flower client. And in that Flower client, you would implement a number of methods. The most important ones are fit and evaluate. In fit, you would receive model parameters from the server. You would update the local model with model parameters. You would then do the local training, and then at the end, return the updated model parameters back to the server. Evaluate works in a fairly similar way. We receive model parameters from the server. We update the local model parameters. Then we evaluate the updated parameters on the local data. And then we return simply the evaluation results back to the server. And all of that is wrapped up in a client app. So with that, let's actually run the project. So we can, we've seen what the project looks like. We can FLWR run. I should look at my screen and typing. So this starts up a local simulation where we have the 3 clients that we configured earlier, and it it starts virtual clients. This means each of these clients can use most of the resources you have on your local machine, and then the Flower simulation engine takes care of running the first client, then running the second client, and then running the third client. And we can see that, for example, in this first round, we select 3 of these clients. We receive the clients do the local training. We receive 3 results, and then we aggregate those results. We do this for 3 rounds. So each of these things is called a round. We go to the client, collect updates back, and aggregate them. And then in the end, we get the performance of the final model and over each of these rounds. With that, let's go back into the slides and wrap up before we run out of time. So that's what a Flower Hello World looks like. Essentially, what we've built is we could run this, for example, on a Raspberry Pi. We have 1 Pi, we have 2 for the server, we have 2 additional ones for the clients. They have some data on it. They are connected via Wi-Fi, for example. They run the Flower client nodes, and the other one runs the Flower server nodes. We then have a data scientist who wants to use this federation. That data scientist creates the server app, creates the client app on their machine, and then calls Flower run. And this causes the app to run all of these devices. Now, this is multi-run capable. So you could also have a second data scientist who does the same thing, and a third data scientist who does the same thing, and they could all use this infrastructure together. I should give a shout out to the Flower community, because the Flower community is just great and super active in this space. So here's some impressions. We run some community events. The Flower AI Summit has become the world's largest federated learning conference. There are thousands of developers in our Slack channels and creating many open source projects themselves. And it's a really rich area to look into if you want to get some inspiration. And as next steps, and to wrap up this talk, I want to leave you with Flower.ai. This is sort of the main page if you want to learn anything about Flower and federated learning in general. We have a fairly comprehensive tutorial that walks through many different aspects of federated learning. We also recently launched 2 courses on deeplearning.ai. One that is a fundamental introduction to federated learning, and a second one that covers fine-tuning of large language models on distributed data in a federated way. If you like what we do, please give us a star on GitHub. And with that, I want to conclude my talk and also take some questions. Thanks, everyone.
I see we have a few more minutes and we have a few questions in the chat. Should I read them? Or do you have access? Okay, I can read. With federal data, how do you control the quality of data, like to prevent duplicate data on 2 different devices? Doesn't it bias a model?
Great question. In real world federated setups, you often don't have this problem fundamentally of having the exact same duplicate data on two devices. So for example, if you were to run a federation across multiple hospitals, then each of those hospitals would only have, for example, radiology images from their own patients. So the hospital is the one who makes the original scan, and then only that hospital actually has the data. Now, in some other settings, there is some potential for duplicate data. So in those cases, you can combine federated learning with federated analytics to understand how data is distributed on different devices, how data is distributed across different organizations, and get some really good metrics that help you understand whether there's some issues you want to investigate. And that is, it's usually you don't just use federated learning on its own, but you would combine it with things like federated analytics and also other data quality measures on wherever the data sits. Yeah, but it's a great question.
I see we have one more question. Does Flower support any federal pre-processing, for example, by triggering local data cleanup scripts or checks on local machines before learning?
Yes, it does, absolutely. So the Flower framework is fairly flexible on what you can do on the client side and on the server side. So your clients, they can virtually call into any kind of local data processing that you want to do. The Flower client essentially just gives you a hook point where Flower can call into whatever you want to do on the client side. So if you have existing scripts, if you have existing systems deployed, things like that, you could build a small adapter and have the Flower framework just call into that existing system, and then let that existing system do the pre-processing and do any kind of other things. So this is, for example, also useful if you want to build a federation across organizations where each organization has different data storage systems or so. You could write an adapter layer where then when the task comes in on the client side, the Flower client would call into this adapter, and this adapter would be specific and would be custom on each of the clients. So you can integrate with arbitrary third-party systems.
Thank you for answering that. One more question. What happens when one of the distributed devices is down or offline during the training?
Yes, that absolutely works. So there's different ways to handle this, and it depends quite a bit on the setting. So in a mobile setting where you have a large number of participating devices, you would, if a device goes offline during the training, you would usually just ignore that device and say, you would oversample a little bit. So if you want to have 100 results, you would maybe sample 150 devices. And then during the training, 50 devices can go offline and you can still complete the round. If you receive less than 100 results, less than you want to, you would just discard the entire round, sample a new batch of devices, and then start the round again. But you could also, in other settings, you could also send a task to the device would do the training, and then after that, the device could do the training offline, of course, and then after that, go online again and submit the results back to the server.
I see we have time for one more question. And do we need to encrypt or decrypt the data while aggregating the data on the server?
So the key thing is we don't aggregate the data on the server. The data remains wherever it originates. So in that place, we don't need to encrypt the data because the data never moves. The individual clients, those organizations or those user devices, they never have to hand over the data to someone else. But we instead train the model locally wherever the data sits. And then what we send back is not the data, not the raw training data, but what we send back is only the updated model. The updated model, we can encrypt the updated model. There's approaches like secure aggregation, for example, that encrypt the updated model in a way where the server cannot read the individual model update that's coming from one of the devices, but the server can only aggregate them together and only decrypted the aggregated model. So it will never be able to inspect individual model updates coming from individual devices when you use secure aggregation.